Alright guys, let's start our week 2 lecture for manual transmissions. Per the norm at this point, in announcements we've got the lecture, so I've attached the Word document for my worksheet and then another discussion here. Please text me, call me, email me, however you can get a hold of me. A response by Friday. We have a couple questions going on down there. So, close that and get into my worksheet. So who can tell me the equation that we discussed last week for figuring out gear ratios? Driven divided by drive. Right here, please remember that for your test. So that's going to be really any gear ratio ever. Where are we going to have gear ratios in the vehicle? Well, that's really the whole purpose of the transmission, but we're going to have some more. The rear differential or front differential. And sometimes if you're playing Forza or Gran Turismo, they'll call that the final drive. And that's the last gear ratio. And that's a fixed gear ratio, right? That one doesn't change. At least not on the fly. There's no selector in the vehicle to change that gear ratio. If we are talking about a four-wheel drive with the transfer case, there will be some more gears, and which will allow us some more gear ratios within it. But in a standard two-wheel drive vehicle, any selection we're going to have for gear ratios is going to be in the transmission. And any automatic or manual, really we're all achieving the same purpose, to allow the drive wheels to go a different speed than the engine, right? So we don't necessarily need a transmission to make the car go. Last week we talked about a clutch, and the purpose of the clutch was to allow the engine and the rest of the drivetrain to disengage, right? So the vehicle could come to a stop and the engine wouldn't stall. An example of a vehicle that does not have a transmission is the top fuel drag cars. Those skinny, long drag cars that do, I don't know what they do, 6-second quarter miles or something insane. They don't have a transmission. All they have is a torque converter, and we will talk about torque converters in detail next month when we go into automatic transmissions. However, for our passenger vehicles, we're going to need some selection. We don't have a tremendous amount of torque, and we want to achieve a high fuel economy. We want to be able to say my car gets 30 miles to a gallon. So we're going to need some selection. And that's basically this first page here. The manual transmissions that you've driven, I dare say, have never had more than 6 forward gears, right? Most of them are 5 or 6. Some of the older vehicles will have 3 or 4. The reason for this is a manual transmission will always be smaller than an automatic. However, it's longer, and it's difficult to have enough room to make more gears, to add more gear. So 6 is kind of standard. Even my bike doesn't have more than 6. And you'll understand why automatics go up to, I think 12 is the highest I've heard of, but it's not uncommon for passenger vehicles to have 8 to 12 forward gears in an automatic. And that's different because those gear sets are smaller and they're compounded in a different way. But we're going to get into all that today. On this first page, we've got, and you've got to say it this way, it's a 5-speed. Well, that means how many gear ratios? There's at least 5 forward gears. So you hear people talking about that. Or if you hear someone say it's 6 forward gears, implying that there's 2 more, right? There's going to be a reverse gear, and then there's going to be neutral. So what is neutral? Why do we have it in the car? Is it important? And when you select neutral, what gears are actually being engaged? And then I would further spin your brain. You get in an automatic and it has PRND. One of them is neutral. But what's the difference between neutral and park in that automatic? They seem to be about the same, right? So before we get much further into this, I kind of wanted to go backwards in time and talk about the misshifts from last week. And I kept asking you what's really going on. So if we look here, whatever the engine RPM is, and we know there's a cap to that, right? It cannot, shall not exceed. So let's go, this thing idles at, move it up a little bit, idles at 800. And we'll use something fancy, a Honda engine that goes to 9,000 RPM. What's going to happen if this engine RPM exceeds 9,000 RPM? Well, bad things are going to happen. The older engines that did not have a rev limiter, if it was allowed to exceed whatever RPM and it was carbureted, then we'd run into a lean condition. And you guys remember from engine performance that lean is very dangerous. If the engine runs lean, it could detonate and explode. That's really the reason we have rev limiters now, is the computer just won't let you go beyond whatever is safe for this engine. The other thing that happens is you could spin a bearing. When we removed the crankshaft from that engine in the lab last month, and I showed you guys those half circle shaped bearings, the bearings were in the main caps. And when someone says spin, or hey, I spun a bearing, now my engine's knocking, that half moon, half circle bearing will literally rotate up into the block, not where it's supposed to be, not creating the correct oil pressure, not lining things up, and that will really ruin an engine quickly. So this is important. This is a really good way to ruin an engine, misshift, and then the RPM goes through the roof. But I wanted to talk about how and why that was happening. So in those videos where the guys were drag racing, we can assume that they were shifting with the engine probably at its RPM limit. And the idea is when you shift up into the next gear, that should create a situation where the engine can engage at a lower RPM, so you can again run through the engine's power band. So if we miss this shift and I'm aiming for third gear and I accidentally grab first, when I let this clutch out, it's going to cause the engine to rev up. Now let's take a moment and I want you to really understand what's going on here. This engine is tied mechanically to this transmission because the clutch is fully engaged, right? So it should be that the engine is driving the clutch, which is driving the transmission, that's driving the wheels. That's how it's supposed to operate. If we put your manual transmission on a hill in whatever gear, let's just say we're cruising along in fourth gear and we hit a really steep hill, and gravity starts pulling us, momentum speeds the vehicle up. Without touching the accelerator pedal, the momentum of the vehicle is going to cause the engine to rev up, because the drive wheels are attached mechanically to the engine and they are accelerating, which will cause the engine to rev up. On the flip side, you've heard of engine braking, and this is the idea that I'm going to shift in such a way, so downshift, it will mechanically link the engine to the rear wheels, and without me giving it throttle and asking for more power, it's going to rev the engine up, but the engine has to fight the compression stroke, and that is why you get engine braking. When we talk about my sport bike, if I shift incorrectly and dump the clutch, it creates so much engine braking it nearly wants to throw me over the handlebars. In those drag racing videos, we saw the front of the car nosedive and the back wheels come off the ground, and those were all front wheel drive vehicles, so that makes better sense. But we're suddenly now trying to rev the engine up against its want or need or desire, and it doesn't like that. So when that happens, something will snap. Hopefully, and this is a terrible thing, hopefully it's a drive shaft or CB axle that will snap. In those videos, the drag racing videos, we saw fluids coming out of the bottom, so that's safe to assume either a piston came out of the block, or that was coolant, or because a manual transmission doesn't have much fluid, so it's probably not the transmission fluid, and that absolutely sucks. So I found this. I think this is pretty cool. I'll put this right here. This is a calculator. So let's fill it in here. Ring and gear, ring and pinion gear. So that's your final drive, your rear differential. We'll just stick with the 3.73 because that's a nice common number. For tire height, let's figure you've got 18-inch wheels and there's a couple inches of rubber. We're just going to make this a nice, happy number. Engine RPM. So let's do Chris's new Challenger, and the rev limit will be something like 6,000 RPM. And in second gear, and I looked this up, a Tremec 5-speed, the gear ratio is 2.07 to 1. So let's think about this. We're in Chris's car, we're in second gear, we're at 6,000 RPM. What do you think miles per hour we're traveling? Second gear is not real fast. I haven't clicked it before, so I don't know. I'm guessing 6,000 is pretty high. I'm guessing 30 miles per hour. Let's see. Ooh, 46. So this is interesting, and you can see the relationship that's causing this, but my point with the misshifts is if we do this backwards, if I took these numbers out, and this calculator won't allow me to, but if I was doing 46 miles per hour and then I plugged in a gear ratio here that was something like 4 to 1, something closer to first gear, this calculation would yield an RPM of like 10,000 RPM. And for reasons we just discussed, it really doesn't want to do that. So that's what was going on with the misshifts and transmissions and engines blowing up, is this mechanical link here causing something to speed up. So I found this guy. I think this is cool. Provided by Tremec. They make a lot of transmissions for American vehicles. So let's plug this in real quick and check it out. So let's pretend we're cruising 2200 RPM. Final drive, we'll do that 3.73 to 1 again. Tire height, we'll stick it with 20. And it's already got what the gear ratios are in this 5-speed transmission. So let's hit calculate speed. And assuming we were doing 2000 RPM, in our final gear here, fifth gear, we would achieve about 50 miles per hour. So let's see what RPM it's going to take to get you up to 80 so we can cruise on Highway 35. So let's bring this up to 3500. Calculate 80. There we go. So with this 5-speed, we're not getting fantastic fuel economy because just doing 80 miles per hour requires us to do 3500 RPM in our final gear. I wonder if it's going to let me add another gear here. What if we did that? Put a, ooh, yeah, 0.5. And there we go. So then, if we had one more gear, a 6th gear, we could bring this down. Go back to 2200. Not quite enough to do 80. 2400. 76. 2600. There we go. 80 again. So we've lost almost 1000 RPM because we added another gear ratio here. And this is a very common thing here for 4th gear to be a direct 1 to 1. So this is a direct drive situation. This would be if you only had one gear or no transmission at all. What the car would do. Top speed of 41. And because there's no torque multiplication happening, it would take forever to get there. But I thought that was cool. So we'll go back to this guy. No, let's go back to the lecture. So grab your worksheet. Actually, this is what we need to do right here. So let's talk about what kind of transmissions we have before we move on. There are two main types, right? You've got an automatic and a manual. What makes an automatic an automatic? The fact that it has planetary gear sets. So that's this guy on the left. The three main components here that I'm just going to tell you, and we'll go over a lot more next month, but it's so simple. In the center, we have a sun gear. Rotating around the sun gear are planet gears. Oh my gosh. And then the outside is called the ring gear. There's a carrier in here, and the carrier is helping keep these planet gears fixed because I don't want this guy to rotate and then get too close to this guy and bump into that guy. So we're making sure that they all stay equally spaced. So when we talk about these three main components, it will be the sun. I call it the carrier, which is this carrier and its planets, because we're going to use that as one factor in our gear ratio. And then this ring on the outside. And what makes an automatic is that it has a torque converter, not the fact that it changes gears by itself, because dual clutch transmissions change gears by themselves. CVTs, you throw it in drive and it goes. And there are some manual transmissions that are shifted electronically by the computer. And they're not great, but there are some. So that's what makes an automatic an automatic. When I ask you again next week, you'll say an automatic has planetary gears and a torque converter. So what makes a manual transmission a manual? Compound gear sets and the fact that it has a clutch. So let's stand right here. Last week when I asked you what was the purpose of the clutch, your answer should be to allow the engine and transmission to disengage. So next month when I ask you what is the purpose of this torque converter, the answer needs to be to allow the engine and transmission to disengage. The torque converter is cool because you won't believe it, but it does do some torque multiplication. However, because it's a fluid coupling, there is some power loss, which creates a lot of heat. So, one way, half a dozen one way, six another, which one is best? And in addition to our automatic and manual, we have these two, CVTs and a hybrid. If you've been in a CVT, you probably have some feelings about it. Most people dislike CVTs. When I worked at Nissan for a little while, and I'm not making this up, had customers come in and say, there's something wrong with my car. It's stuck in first gear. And I'd say, wow, how did you get here? And they'd say, oh, I took the loop. Well, how fast were you going on the loop? 8 miles an hour? No, I was going 60 miles an hour. Well, there's no way you were in first gear doing 60 miles an hour. That's impossible. And so I'd go out and look at the vehicle, and the vehicle would have a CVT. And the customer was so excited when they bought the car. They didn't know this. They don't know what it is. So if you've not been in a CVT, you put it in drive, and then you hit the accelerator pedal, and it never shifts. There are no gear ratios in here. It's a rubber band, and it's actually really cool. They first came out with this technology for F1 cars, and it was so fast that it got banned in F1. And what I would say to you, I know you don't like it, I know you don't like the way it feels, it's no fun to drive, but if you're going to argue that they suck for performance and they're not strong, if it's fast enough and strong enough to go in an F1 car, then it's pretty cool. And then in addition, we have hybrid transmissions. If you didn't know, the part of a car that makes it a hybrid is the transmission. And really, this is a CVT combined with some big giant motors, but we'll get into that later. The one other distinction here is for this manual, we have an H pattern or a sequential, which I spoke briefly about last week. I do kind of want you to look at the size difference on these two guys. This automatic is shorter, but much bulkier than this manual. Is longer, but thinner. The automatic transmission is full of fluid and is going to be much heavier than this manual. How we tell it to shift on both of these are going to be similar, either a linkage or some cables. So whichever way you slice it, you're going to have those components. The thing about this automatic having fluid, though, is that fluid has to be changed regularly, otherwise you have problems. The manual transmission will last much longer and doesn't require nearly as much maintenance. So let's get over here. Planetary gears. These are very common in mechanical engineering all over the place. So if you Google planetary gears, you'll find it in, if you're Wife or mom has a mixer in the kitchen. It's got one of those. Dump trucks use these. Helicopters, planetary gears are super common because they're super efficient. And what's interesting is I'm just going to note this quickly. These gears are always meshed together. When you select drive, it does not disengage one gear set and engage another to achieve whatever, what we like to call first gear. These guys are always engaged, and because they don't disengage and re engage, there's no wear and tear like what will happen on this manual transmission, which we're going to talk about in a second, how it engages. Every time you engage a gear in a manual transmission, you are taking some life off of the synchronizers. And you've probably heard or been in a vehicle where it just doesn't want to shift into second anymore, or it just doesn't really like to downshift into first anymore because those synchronizers have been worn out on that manual transmission. In an automatic, that never happens. These gear sets never break down and wear out in an automatic, which is kind of a cool thing. So we call it a compound gear train because we need several gears. We can't just throw one gear. Let me bring up the drawing here. We can't just have one gear, and I'll show you why. Give my little pencil here. So we've got gear number A, and he's rotating this way, right? Well, that's cool, but because there's only one of them, we don't have any gear ratio going on. Gear A, right? So we need to mesh a second gear to it, and I was supposed to draw that as a different size, so this makes sense. So we have a different gear here, boop, and these dudes are meshed together. And because they're different sizes, we're going to achieve a gear ratio of whatever, right? Which is the whole purpose of this. The thing that's interesting, though, is if this dude is spinning this way and we're meshed together, that's going to cause B to rotate that way. I may not want that. Maybe I want everybody to continue to rotate clockwise, which will require one more gear so that the rotation is fixed back the way we want it. So when we look at these gears here, there is always a counter shaft. And check this, if you can see my mouse right here, there's a third gear right there, and that's so the rotation gets fixed. So I want you to read this. I'm going to skim through a little bit of it. Also, good news, this is going to be a short lecture. This one doesn't take very long to explain manual transmissions. Fourth gear is normally 1-to-1 or direct drive, so whatever engine RPM you are doing is what the drive shaft is doing. Now that's not what the wheels and tires are doing because there's another gear ratio in the differential, and that's going to change things. Also, if we change the tire and wheel size, you know that a lot of vehicles, the speedometer will be wrong. Well, that's, of course it is. It was working off of the output shaft here. Most vehicles use the output shaft to determine vehicle speed. And it knows the math because an engineer made it, and they know the gear ratio in the final drive is whatever. And the vehicle came equipped with, 16-inch wheels with modest tires. So then you're going off road, so you put, giant tires. You put some big old mud tires on it, and the diameter now is 2 inches bigger than what it was. Well, nobody told the input shaft sensor this, and so it's continuing to do its math, and it's rotating at whatever speed that is supposed to be 60 miles an hour, and really you're only doing 50, or vice versa. So if you're thinking about changing the wheels and tires, just be mindful of this. There are a lot of workarounds for this where you can correct it, but just be mindful. I had somebody put sprockets on my motorcycle one time when I was real young, and they went down a tooth, and what that does is create a final drive situation where I have more acceleration and less top end, but they didn't tell me that they had done this. So a month later, I was cruising with some guys, and I was like, man, we were really flying. We were doing, 90 or something, and the guy was like, dude, we were going the speed limit. What are you talking about? And then my friend piped up, oh, I forgot to tell you, I changed the sprocket, and now your speedometer is off. Oh, thanks, dude. I wish I'd have known that. So just be mindful of that. Fifth gear is normally an overdrive situation, and the term overdrive in itself is tricky. People misuse this term a lot. Any overdrive situation is one where the output shaft is going faster than the input shaft. So let's go back to this guy here. Engine RPM is, let's just pick a number here. Let's go. You're doing 2200. 2200. And now the drive wheels, well, let's not go there. Before the differential, so the drive shaft itself. So we'll put you right here. Drive shaft is now doing 1800 RPM. This is an overdrive situation. I am now driving the output more or over what I'm doing with my input. This is fifth gear, sixth gear, and when we had situations where the gear ratio was high, so like 4.1 to 1, first gear, we're sacrificing distance for torque, right? Torque multiplication, but it won't go nearly as high top end. That would be an underdrive, and then we hit direct drive where it'd be 1 to 1, and then any overdrive is this. Don't confuse overdrive with torque converter lockup, which we will talk about next chapter, next month, next module. And in some vehicles, namely pickup trucks, there might be a button that says overdrive on and off. There might be a tow haul button on the gear selector. That's not actually overdrive, that's torque converter lockup. And I don't want you guys to get confused, but overdrive is very simple. Anytime the output is overdriven, driving faster, more than the input, that's an overdrive situation. So here we've got more examples of gear ratios. First gear is normally a very high number. As we approach fourth, it gets close to 1. In this particular vehicle, direct drive is fifth gear, and then sixth is an overdrive. And then we have reverse, which is a different gear ratio. A lot of times you'll have reverse either be first gear or second gear. And in real simple terms, in order to create reverse, we just eliminate this guy. No C. So if this was second gear, B right here, if this gear set achieves second gear, and I eliminate the counter shaft on C, now my output is reverse, equal to whatever second gear is. So if you've been playing around in reverse, and reverse normally doesn't achieve a very high top speed, it's because it's normally first or second gear in order to make this compound gear set simpler. So I thought that was cool. This transmission, this Tremec, what number are you? TR3160, can be found in a Cadillac ATS, a Camaro, and a Mustang. And I would ask you, why are they all using this same transmission? I get Cadillac and Camaro, or Cadillac and Chevrolet, because those are both GM products, so it makes sense they're going to try to reuse the same transmission in as many products as they can. But Ford is also using it. And this answer is because how many manual transmissions are at your dealership right now? Not very many. So instead of Ford engineering their own transmission and then have to support parts and service and books and all this, they just called Tremec, which is not Chevrolet and not GM and not Ford. It's its own company. It's kind of like, if you guys are familiar with Dodge, the diesels are Cummins engines. Dodge doesn't build those. They have a relationship with Cummins. So here we have GM and Ford both. Hey, Tremec, can we get one of your transmissions? Because we're only going to sell 10 of them. So this transmission is actually very popular. If we go to look, there's only 3 or 4 manufacturers that still make manual transmissions because you just can't get them anymore. I really like this here. This is the speed, miles per hour, that we can achieve in whatever gear that we're in. And I really like this because if we look at fifth gear, and I asked you at fifth gear, If we took off at idle, like we're standing still, 0 miles per hour, and I asked you to shift into fifth, what RPM would it be at? Well, according to this chart, idle is probably right here, 800 RPM, where this line starts. It won't do 0 miles per hour. It won't do 5 miles per hour. It won't do 15 miles per hour. This is really cool because there's an engineer somewhere. The engine in this Mitsubishi, so we can imagine it's a small 4-cylinder, doesn't create enough torque to launch the vehicle in 5th gear. It will stall. It won't even launch the vehicle in 3rd gear without slipping the clutch a lot. So I think this is cool because 1st gear will take you from 5 to about 35 right here. What do we get? Maybe 45 in 1st gear. If we shift into 2nd, at any point of this between 15 and, see, 2nd goes all the way to 75, we'll be okay. And then we could go straight into 5th if we wanted. This is cool when we talk about if the gears are long or short. So 1st gear is really short, and we say that, look at the span of miles per hour, and I know it's kilometers here, but whatever. Look at the rate of speed. 1st gear doesn't go, we don't have a long distance. There's that word, force and distance, with 1st gear. 5th gear is a very long gear because we could possibly be from 25 up to 205 kilometers an hour here. So I'm glad that I found this. This is the actual Mitsubishi came in the book thing. And no, your car does not want to launch in 5th gear. Alright, so before we jump into that, you like that shift knob? Watch out, dude, he's a ninja. Before we get into that, let's go back over here and talk about the manual transmission. So input shaft is this green shaft and output shaft is this yellow shaft. And when I was first getting into this, I thought the counter shaft, or here it's labeled lay shaft, was the output shaft, because when we look at a transmission, this line here going in and this line going out appear to be the same shaft. So I've got a picture somewhere. Bear with me for just a second. Boop. Nope. This guy. So in this compound gear set, where my mouse is would be input shaft. It travels down to one of these gears, comes back up to the output shaft, and then leaves. So this is not actually connected through the center, which I didn't understand. That's a CVT, or that's a hybrid. That's not the same. But let's not open the same one again, retard. Here we go. Right here, I thought that this input shaft and this output shaft were one shaft running through the center, and I thought that this counter shaft down here was the output shaft, but that's not actually how it works. So this right here, this first gear set, is the first rotation, and then let's pretend that this gear set here is whatever gear we've selected. So power would flow, this is the clutch, it would go input shaft down to the counter shaft, and then if these two were engaged with each other, back up, and then output shaft. And then you shift out of this gear, it disengages, these two are no longer splined together, and you spline these two together to achieve a different gear ratio. Power flow would go this way, down to the counter shaft, back up to the output shaft here, and then out. So not very, very complicated, not very big, nice and strong. However, these collars and these synchronizers that have to engage and disengage are going to wear out over time, especially if you're rough on your transmission. So we've got our gear selected. Let's pretend this is a very, very, very simple engine here. Our transmission input to the counter shaft, and I have a selection here of either first or second gear. So neither of them are actually engaged until you push the gear select fork. And then everybody take your hand out and do the H pattern with me. In order to achieve first, we're going to go left, and your options are forward or backwards, right? So in this one, if this was a transmission in your car, there would be no left. It would only be forward and backward. And forward and backward would either engage this set here, or this set here. Okay, so if we pull up the transmission here, anytime we have a collar in between two, that's going to be two gears that are next to each other. So third and fourth, right? Because those are forward and backward. Fifth and sixth, if it has it, those will be next to each other. They don't necessarily have to be in order, first and second, and then third and fourth, and then fifth and sixth, because the left and right changes which selector for. This is a very simple illustration because we've only got the two, but if we had 6 gears, there would be 3 of these, right? So that you could go left, and that would give you the option of either first or second. Leave it in the middle, which would be third and fourth, and then move it to the right, which would give us fifth and sixth. This explains why one particular gear will wear out. It's always second gear. So you move it to the left, that engages just these two. You pull it down, and it slides the collar this way. And these little teeth that are sticking out are the synchronizer to try to help this collar and that gear line up and mesh before it fully engages, so you have a nice smooth shift. And if you're shifting really fast, really hard, your RPM and output are not the same, then that's going to tear those synchronizers up. Because we have these synchronizers, though, you don't necessarily need the clutch to shift. I spoke about that a little bit last week. So you absolutely could go from first to second without using the clutch, but when you do that, we're keeping in mind that one thing I can control is engine RPM. The vehicle speed is determining what my output shaft is doing, right? So let's pretend that's this gear here, boop, that's vehicle speed. I really can't change that. I could use the brakes to slow down, and that would change the output shaft speed. Engine speed, if the clutch is fully engaged, that's going to determine the RPM of this guy, and I can control that with my accelerator pedal. So in order to get these two to line up, I can rev or let the engine fall in RPM until those guys are close enough that it will engage smoothly. We use the clutch because by disengaging the engine, it will allow this gear to rotate freely, which makes it easier for the synchronizer to engage, but doesn't make it fully, you don't have to have it. So when I told you guys that the 18-wheeler truck drivers don't use their clutch, that's why. And that's part of what takes them so long when you're behind an 18-wheeler and he goes, bop, bop, bop. It takes a second for him to find the correct wheel speed and engine RPM for him to line up smoothly. So here we've got the gear selector has now splined with these and is engaging this output shaft to this gear selection. So before, on this picture, this guy and this guy and this guy and this guy, we're all rotating together, but nobody's actually tied to this output shaft right now, right? But here, we're going to engage what I'm calling second gear on this gear set. Now the output shaft is splined to this gear set, and I'm going to achieve my gear ratio of whatever second gear is. What's going on over here? Let me close these. Cool. So here's some cables. Most transmissions now have gone to cables. They last longer, they're flexible, especially because the transmission is normally now in the front of the vehicle. So on an older vehicle, and there was a gear selector, like right here with the Stutes Katana, that was literally on top of the transmission. So when my picture here, this gear selector, I mean, it was just bam, there's the transmission, it's mounted straight to it. But if we put the transmission in the front of the vehicle, like a front wheel drive vehicle, we're not going to be able to do that. The gear selector would have to be on the passenger side of the hood. So we've got some cables or some linkages to connect these guys. So let's move forward. The flattened portion at the bottom of the shifter fits into the U-shaped cutouts and several shafts called shift rails. So check this guy out. If we've got 6 forward gears, there are 3 shift forks to slide the collar and the synchronizer onto gear set 1, gear set 2, gear set 3, and then this transmission is going to have reverse. So that means there will be 3 shift rails and 3 shift forks. Will they fail? Absolutely, especially if you bang through the gears real hard. The gear sets themselves shouldn't fail because they're splined together all the time, but this collar that slides back and forth with the synchronizers will wear out. And my picture of one here, anytime you go to take one of these apart, if I need to get to this gear ratio here, this gear set, I can't get to it without disassembling the entire thing. So keep that in mind, service. If you're going to rebuild one, you are rebuilding the whole thing. Hey man, my car grinds in second gear. Well, I can rebuild it for you. Cool. And you go to parts and you ask for every synchronizer and seal in this transmission. And the labor for replacing the synchronizers on second gear will be the same labor for synchronizers on sixth gear, and so on and so forth, because there's just no way to do one of them. You're going to do all of them. So, keep moving here. There's typically a shift fork for each 2 gear selections. We just said that, blah, blah, blah. This is where the U-shaped cutout comes in. The U-shaped cutouts are located on the selector shift rails. And to select one, the shift lever must be moved to the side to engage the U-shaped cutout in one of the shift rails. This dude right here. And then this slides over the collar and pushes the collar back and forth. So it's really pretty simple in the way that it works. Things to listen for while diagnosing a manual transmission. We have to decide if it's the clutch, if it's the selector, or if it's the actual transmission. So when we talk about the clutch, it could be the clutch material, the pressure plate, the throwout bearing, or the hydraulic circuit. If we talk about the selector, here, it could be these cables, and a lot of the cables have an adjustment on it. So I put a clutch in a Sentra, and the mounting bracket for this selector cable got bent. So you get in the vehicle to drive it and go left to find first and second, but the literal selector here, this lever, would travel too far to the left because the cable wasn't where it was supposed to be. So that's going to be rare, very uncommon. By itself, it's never going to happen. It's not going to bend itself. What is cool though is I have had 2 vehicles where this cable came apart. So the gear selector here would feel like it went left and right, but because the cable wasn't attached to the top of the transmission anymore, it wasn't making, where's my forks and stuff? It wasn't making any of these things actually move in the transmission. So you thought you were shifting into first, and because the forward and back is a separate cable, there'll always be 2, right? One cable is for left and right, one cable is for forward and back. So you would go left and forward. The left and right cable was broken, but the forward and backward one was working correctly. So you thought you were going into first, but really you were shifting into third. And it would stall the vehicle, and it would sputter and slip the clutch and everything. And those were both on Ford Escorts, maybe Escapes, either way, where they were coming apart. So interesting. And then if you haven't met yet the shift interlock on an automatic transmission, you will, and we'll talk about that more next module. So differentiating between a clutch problem, a gear selection, and a manual transmission problem is important, because what am I taking apart? Do I really need to disassemble this transmission to find the problem, or is it the clutch, or is it the gear shifter? A simple way to ensure the long life of your manual transmission is to not be banging through the gears. Don't force a gear if it's not ready. Try your best to not slip the clutch. And then if you didn't know this, it's not very good to leave the clutch pressed to the floor for very long. When we spoke about the clutch last week, the part that moves is that throwout bearing. And if it's constantly pressed against the pressure plate, it's wearing itself out. Whereas normally, you let the clutch pedal go, and the pressure plate squeezes everything together. So the pressure plate is really supposed to handle the load. The throttle bearing shouldn't be engaged very often. So if you come to a red light and you leave the transmission in first gear and you push the clutch in, of course the engine will be fine, it's disengaged, but you'll wear that throttle bearing out quickly. So it's one of those things you try to not have the clutch engaged when you're not using it. The other thing is, yes, there is fluid inside of it because there's a bunch of gears, and we want to make sure that it gets properly lubricated. The transmission itself is going to have a vent on top. So just like in, it's not here, just like in the engine, we have a positive crankcase ventilation system. On this transmission, we're going to have oil in the bottom, splashing on the gears, and it's going to aerate and create pressure. So on the top of the transmission, there will be a vent. So, oh, it's little. Blow that guy up. So, you went off-road mudding in the Cherokee, and you submerged the transmission in water, and water got into the vent on top, and now the transmission is full of water. Water is not a great lubricant, and it will absolutely wear the transmission out. Differentials work the same way. They also have a vent on top, so just be mindful. If you go out playing, you need to check the fluid when you're done. And a scan tool can help you diagnose manual transmission errors by watching what information. So we'll go back to my picture here. There will be an input shaft RPM sensor and an output shaft RPM sensor. And if we have a problem where I don't think it's engaging second gear, well, I could watch the input and output shaft speed sensors and it would tell me what's actually going on within the transmission. So if you get into a situation where you think something is broken wrong, maybe you think the gear selector shaft or fork is broken, we could be monitoring the live data, what's going on inside the transmission while we shift through gears. And you could put this guy up on a lift with the engine running and shift through the gears and say, watch it with the scan tool, and that would help you hone in on what's really going on. Here we've now got 5 gears and a reverse. So we have our 3 collars, 1, 2, 3. And then on this one, reverse is an added idler gear. And for this reason here, it's to make sure that so let's pretend C is still there. So 1, 2, 3, but we've added a 4th guy here. So on this picture, take my X's off. Now what it is called the idler gear there in that diagram is creating the opposite rotation to this output shaft. If you're moving forward and you suddenly shift into reverse, and no matter what you do, you're going to blow the transmission up. So you say, well, what if I have the clutch in? Alright, that's fair. So this was all rotating, this was all rotating, this is all rotating. We're moving forward. This output shaft is tied to the rear wheels. I now select reverse, even if this input shaft is no longer connected to the engine because the clutch is pushed in, these gears are still connected and are still moving forward, and then you shift into reverse and it's not going to be happy because it's being driven by the drive wheels. So if you know somebody that likes to put it in reverse, start backing up, push the clutch in, and then jam it into first before they stop the vehicle. That is going to destroy this idler gear, the synchronizers, and this gear set here that is reverse. I've seen many customers do it. Don't be that person. You will absolutely ruin your transmission. And one more time on this diagram, this is a realistic what it actually looks like. What I want you guys to remember is that this is the input shaft section here. This is the output shaft section here. It looks from the side like it's all one, but it's not. It's split, just like this diagram shows. And this down here would be your counter shaft. We have to have a counter shaft for this reason. And the synchronizers that slide the collar back and forth are your wear and tear item. And yeah, that's manual transmissions in a nutshell. Not a whole lot to it, pretty simple. It can be a little daunting to diagnose for this reason right here, because you can't see it from the outside, and if you go to disassemble it, you're disassembling the whole thing. My advice to you would be, if we have to do exploratory surgery to find out what's wrong, you really want to have decided what was wrong before you take it apart. God forbid you take it apart to try to find what's wrong and none of it looks visually damaged to you and you're not sure, and then you've got it all apart and you're not sure what to replace. So with this diagnosis, we've really got to kind of nail it down before we get into disassembly. Um, Outside of that, I gave you your discussion questions. Make sure you get started on CDX. Next week, guys, we're going to be back in class. And I think that's going to be, they're cleaning everything up today. And I think that we're supposed to 100% be in class from now on. So, yay, exciting. I look forward to seeing you guys next week. If you have questions or concerns, you got my number, call me. And I will see you guys next week.